So, hello and welcome to lecture number 12 on convex analysis, and today we are going to deal with proximal algorithms. So last lecture we worked with subgradients and derived the so-called subgradient method, or the projected subgradient, or there's a okay, so this is related to the exercise, so probably I'm not fast here. Okay, sorry. So the subgradient method, which does the projected subgradient method, which can solve the minimization of a merely convex function, of which you can know, which you can access subgradients at any point, and for which you can project onto the constraint set. The method does simply at the point grab a subgradient, go into the negative direction of it, and projects back onto the set. So it's this method has not too many nice properties. One of the nicest properties is that it works if you choose the step sizes properly. And one way is to choose it in a non-summable but square-summable way, like 1 over k. But the bad news is that it's not even a descent method. The iterates of the values, the function values, may jump up and down, but finally they're going to converge. You can get upper estimates on the best function value which you get in the first n iterates, but these are not very good, and in practice also the method is not very good. Sometimes that's all you can do, but usually it's not the preferred way to do. So I don't have any question prepared for that, but we move directly into the topic of proximal algorithms. Okay, so proximal algorithms is probably the one thing which is really unique about convex optimization. So for general nonlinear optimization, you can always work with gradients and sometimes Hessian matrices and do gradient descent, because you know, in smooth nonlinear optimization, the gradient points into a descent direction, and if you pre-multiply by the inverse Hessian, it's Newton direction, which is even better, and stuff like that. And that is basically what you can do. In convex optimization, we have one more operation which is sometimes really, really helpful. This is the so-called proximal map. And we will see that this proximal map is a great tool. And we're going to start with a lemma, which we should have or could have proven some time ago, which says that the proximal mapping is Lipschitz continuous, and even with constant 1. So if we have f convex and lower semi-continuous, and lambda, any lambda positive, then we have that the prox, so the distance of the prox of at some point x minus to the prox of some other point is bounded by the distance of the points. And this means that the prox operator, so this means prox lambda f is 1 Lipschitz. Okay. I think in the later lectures we'll also call this property non-expansiveness. So because if you have distance to a point, the distance between 2 points does not increase if you plug both into the prox operation. And by the way, this also proves that projections are non-expansive, or also 1 Lipschitz, because the projection onto the convex set C is nothing else than the proximal operator for the indicator function. So this shows also 1 Lipschitz. Okay, and that is what we used in the lecture on the last lecture on projected subgradient method. Okay, so let's prove it. It's actually not that hard. What we use is the variational inequality. So we use the variational inequality from theorem 82, and maybe let me just recall it here. Just a second. So it says that for all y, you have that that x minus x hat times y minus x hat plus lambda f of x hat minus f of y is non-positive if x hat is the prox of x. Yeah. So we use that 2 times in this form with some y and another way around with so we also use y. It said y hat is the prox of lambda f of some y, and then we write down this inequality here with swap roles, which says that then we also have y minus y hat times this yeah, that's true. Oh, sorry, I've got confused a bit. So what I want to say is we get that. Yeah, that's true. Yeah, so we get this here for all x. X minus y hat plus lambda f of y hat minus f of x. This is also non-positive. Yeah, that's what I wanted to say. So this is the variation inequality for this pair. If x hat is the prox of x, this holds for all y, and if y hat is the prox of y, this holds for all x. So what we can do is we choose y hat over here and x hat over here. It's all possible. We can do that. So we can use y hat here and x hat there, and then we add the 2 inequalities. And what do we get? We get that these 2 terms with the f's cancel out totally. So this is positive here, negative there, positive there. And we have to add these 2 guys, and they do not cancel. So what we get is 0 is larger or equal to x minus x hat, y hat minus x hat, plus y minus y hat, x hat minus y hat. Yeah, so what we do is we bring this into one inner product. So we probably swap that around here. And then what we get is, if we swap that, we switch the sign over here, and we can write x minus y minus x hat minus y hat times x hat minus y hat. That's what we get if you combine the 2 inner products here. And this we see now, this gives us actually one inner product, x minus y, x hat minus y hat. And this gives us the norm squared, negative 1. X hat minus y hat 2 norm squared. So we rearrange this by bringing this to the sheesh, I messed it up again. I swapped these guys here, sorry. I swapped these guys, and it's y hat minus x hat, sorry. So this also swapped, but this doesn't matter. It's y hat minus x hat, and it's a positive norm. So because this, we have this with a minus sign here. It's a positive norm. So what we can do now is we bring this to the other side, having x hat minus y hat 2 norm squared is smaller than the inner product, x minus y, x hat minus y hat. And now we use Cauchy-Schwarz, x minus y, x hat minus y hat, and of course 2 norms, and can cancel 1, and this is exactly what I wanted to show. This here is the difference of the proxies. This is also the difference of the proxies. We cancel 1. Norm of difference of the prox, small equal norm of the arguments we had. Okay, so the prox is always 1 Lipschitz, so it's always non-expansive, which also means that it seems not unreasonable to iterate the prox because it's a non-expansive fixed point iteration then. Okay, so what? Let's see. Yeah, this is actually one motivation what one can do. So what we do, we consider the following iteration: xk plus 1 is equal to the prox operator of lambda f of xk. And no, it's in this case I wanted to not use lambda k. I wanted to call the step size as tk f for some tk non-positive. So this is the so-called proximal point method. what we want to show is that the iterates of this here actually do converge towards a minimum of f. Okay, so this seems like an algorithm to solve general convex optimization problems. Minimize some f, and actually the only thing which we need to be able to do is to evaluate the prox operator of that f. And then we can start iterating this guy here, and then we want to converge to some minimum. This sounds cool, but actually it's not. But it will be cool in the afterwards. So at first sight it may sound cool because it always works and it's very, very simple. It looks simple. But consider that the prox has the definition as solving a minimization problem. Actually the prox does is the argmin of 1 over 2 x minus xk plus tk f of x over x. So minimizing f is one thing which we consider difficult, otherwise we would need an algorithm to do it. We could just do it by hand. And now we replace the minimization of f by iteratively minimizing a problem which is kind of the same. It only adds a norm. Oh, it's the norm squared actually. So we're replacing a difficult problem by an iteration where each iteration solves another kind of difficult problem. Seems not a very good idea, but two things. First thing is this problem is a little better than minimizing f itself because it's strongly convex because of this norm squared over here. It's 1 strongly convex. So strongly convex with constant 1. So this is a better type. We're going to see that this is better in later lectures. And the other thing is, even though then it's still not practical because we still need some method to solve this, it may be helpful as a building block for further algorithms. So in the next lectures, we're going to see, or even at the end of the lecture, we're going to see that this operation here is still helpful for complex, for not so simple convex optimization problems, but just as a building block, not as a method in and of itself. Okay, but first prove that this method is going to converge. So it would be good to know. So this is just first kind of descent lemma, which shows that the proximal such a proximal step always reduces the functional value. So xk generated by this xk plus 1 is equal to prox, and then tk f of xk. Then we have that f at the next iterate is smaller equal f at the previous iterate plus, oops, that should be a typo. Sorry. This plus minus, just a second. I will clear it up in a minute. Yeah, it should be a minus actually, sorry. Yeah, it should be minus, of course. And then it's minus 1 over tk, and the difference between the two. So it says that if you do a prox step from some x, you get guaranteed descent, but you don't know how much because you don't know how far you're going to move. Somehow the farther the step is going to move you, the better it seems, but you don't know how far you're going to move in advance. So of course it depends on t. So it's kind of a trade-off. It's not really that you can know somehow what you should expect. Okay, let's prove this. That's also straightforward. You again use the variation inequality to get, I just write it down probably. So in the variation inequality, if in case you want to check, you need x and y both xk, and x hat is then of course xk plus 1, because if xk is x, then x hat has to be xk plus 1. And this shows that if you take tk plus 1 times f of xk plus 1 minus f of xk plus, and then here in this inner product which you have in the variation inequality, you have 2 times the same thing. So like this, and this is actually now the norm squared, and then that's it. You bring this to the side, divide by tk, and bring this to the side. That's already it. So that's actually very straightforward. Okay, somehow we can use this to prove now convergence. So now it looks good. These f values are always decreasing, but as you know, this is not enough. It's not enough to show that the xk converge. This is actually something we don't know, and we don't know, and we can't prove without further assumptions. And we also don't know that this f of xk is actually approaching the minimum. It may kind of stagnate before it gets to the minimum value of f. That's still very possible. So if this is our f, it may still be possible that you kind of stagnate over here and then get stuck at some point. Okay, but the next theorem says this is not going to happen. Okay, now we need f proper, convex, and lower semi-continuous, and by f star we denote f of some x star, and this f of x star should be such that this is the minimum value. So x star is the minimizer, f star is the minimum value. Then for xk generated by the proximal point method, we have 2 things. The one thing is the xk plus 1 is closer to x star. Of course, 2 norms. We've already seen such a property. This algorithm has the same property than the subgradient method, that it moves closer to all minimizers. That's the nice thing, right? It moves closer to all minimizers. Of course, if the minimizers, even if they're unique or not, it doesn't mean that the sequence converges. But if the minimizers are not unique, it's clear that the sequence cannot converge to all of them. And one more thing is that you can also have an estimate on how good the function value is after n plus 1 iterations. Of course, you would have f minus f star smaller equal, and then there is the distance at the beginning to some minimizer, and then you divide by 2 times the sum of all the step sizes. That's what you get. And then you see, well, if the step sizes are not summable, so let's say, for example, constant, then this goes to plus infinity. But it also says, so the larger you choose the step sizes, the better get this estimate. And it also shows if you take the step sizes to plus infinity, you can even be there at 1 step, which is also almost 1 step, which is also pretty clear from this picture here, right, or from this definition. You could also think about this, where the argmin is not affected if you multiply the objective by some t, or by some constant, so you could kind of divide through by tk, and then if you make tk larger and larger, the first term here does vanish, and in the end you're only going to minimize f, and this is what you wanted to do in the first place. So the larger t, the better, at least for one proximal step for in this simple problem. Okay, let's prove this. Okay, it's again variation inequality, but now we use x is xk, of course x hat is xk plus 1, but as y we use x star. We can use all the y's in the variation inequality, and we use x star. And then after a little bit of rearranging, we see that we have f of xk plus 1 is smaller equal f star, which was f of y actually, minus 1 over tk, and now we don't have a norm here, but we have xk minus xk plus 1 times x star minus xk plus 1. So this looks maybe not so nice, because it's not clear what we're going to do with this, but there's kind of a standard reformulation for terms like this, which I always forget and always have to look up. Let's derive it. So the problem is, so we can kind of, these are different in both positions, but the last one is the same. So one of the four is equal. So what we do is we do minus xk plus xk here, and then we have xk minus xk plus 1 on the right hand side as well. So this gives us f star minus 1 over tk, and then we have first the inner product xk minus xk plus 1 times x I switched something. Oh, no, I wanted to switch to plus here. I wanted to switch to plus here, and such that I can switch here to xk minus x star, and then we have a minus here, minus norm of xk minus xk plus 1. Yeah, so note that I switched to plus, so I switched the order around here. Yeah. So this term in total has a minus sign, and it had a minus sign as well here because it's xk minus xk plus 1 and xk minus xk plus 1, and it gets minus norm squared over here. Okay, so that's one thing, and this is already the term we would like to have, kind of. No, it's not. It proceeds a little bit differently. So what we now do is we do something with this term here and try to turn it into something nicer. And there we use a simple fact, which is the fact that for two vectors, the inner product a plus b can be expressed exclusively with norms. Whenever you have this inner product, you can rewrite it exclusively with norms. And just simple algebra shows you that this is norm a squared plus norm b squared minus norm a minus b squared. Of course, all two norms here, but it doesn't matter. That's just the binomial theorem or whatever you like. So we do this here for this with this as a as this as b. So what we get here is that's f star plus 1 over, and then since we replace this by 1/2 of something, we just get the 2 out of the parentheses and put it here. So then we have this equals to 3 norms. The first norm is the norm of that, xk minus xk plus 1, 2 norm squared, plus the norm of that, xk minus x star norm squared, minus this minus that. This minus that, you see that this guy cancels out. It's xk going away, and you get x star minus xk plus 1, or differently xk plus 1 minus x star. And then we still have this guy here, but we have it twice because we have this 1/2 over there. So, okay, we turn the inner product into 3 norms, and in this case it happens that this term here, this a minus b, is also a difference of 2 of the elements here. And I would really love to have a good way to memorize this 3-term equality here, but if I keep forgetting it all over and over again. Because this is so useful in all these derivations, it's kind of used all over the place. The one thing is, you get this term here is here positive, and here it's 2 times negative. So these combine to 1 negative term. And we even just omit it. So we have this, and this gets add up to 1 negative norm squared, and we just omit it. So kind of estimating it further, f star plus 1 over 2t k, and then here you get just the difference of these two guys, xk minus x star 2 times squared minus xk plus 1 minus x star 2 norm squared. Okay, so and from this inequality here we can deduce things. So the first thing is this here, this is larger than that. So we can estimate here further by estimating this from above by f of xk plus, then it cancels out, and we see that this guy here is positive. So since we have xk plus 1 is larger than f star, we can deduce from this that x k plus 1 minus x star 2 norm is smaller than xk minus x star, because this difference here is positive. That's the first thing we can deduce from here. And the next thing is that we observe that we have a telescoping, or it's the same term here with plus and minus sign, but as a next iterate. Previous iterate with a positive sign, next iterate with a negative sign, which means if we sum these inequalities up, once again, as we did for the subgradient method, all the middle terms cancel out and only the first and the last one stays. Okay, and so second is we sum. Let's sum over k from 0 to capital N, and what we get is, if we first rearrange like that, and then sum up. Oh, I forgot the step sizes. We multiply by tk, put the tk's here, by 2tk actually, and then sum up, okay, from 0 to, not to infinity, to capital N. And this is smaller equal to, telescoping sum, we have x0 minus x star, minus the last one, but I just omitted. So there's minus the last term, but this may go to 0 anyway, so I just don't put it there, or make it small anyway, so I just don't need it. Okay, so I forgot parentheses over here, like that. So we already know by the previous lemma, and this is not different from the subgradient method, that f of xk plus 1 minus f star, that is still worse than xn plus 1, the last one here. So this is in decreasing sequence. We saw that in the previous lemma. We have this guarantee, but it's not so explicit. So this will get smaller and smaller. So out of these factors here, the last one is the smallest. And so we can just replace the k by a capital N here in the sum, and then it's independent of sum, and you can pull it out. And hence, so what we can get here is that we have 2 times the sum over the tk's from 0 to n times f at the last iterate is smaller equal x0 minus x star. Dividing by this proves the claim. So this is now nice. So it's a little bit, so the result is technically much simpler than for the subgradient method. It gives you, the method is nice, it gives you guaranteed descent. Okay, you also move closer to any optimal point, which is nice, but it gives you a much better estimate here. It even can be as good as you like. So driving tk to infinity very fast, it gives you a very, very nice, very, very small, fast decay over here. But on the other hand, calculating each step, we still don't have any idea how to do that. So it's a method, it's worth analyzing, and we're going to use it as a building block right now. Okay, let us see how much do we have. Okay. Okay, so why still care about the proximal point? I've told so many times that it's really not a practical algorithm. So then the idea is now the following. Often in convex optimization, you don't minimize just any convex function, but you minimize an objective which has a lot of structure in it. So for example, it may be the sum of 2 different convex functions with different properties. So often the case is that you minimize not some f of x, but f of x plus g of x. And of course, you can always write any convex optimization problem like this. But the thing here is that in many cases, these things have different properties. So it may be, and we'll show an example in the end, that for example, which one taker is that the f may be non-smooth, but it may admit a very simple proximal operator. You calculate prox operators, I guess, for a few things. For example, if it's the 1 norm or the 2 norm, or what else? Probably something else. Yeah, probably also the entropy is a nice thing which can be used here. So there are many functionals for which the prox operator is very simple to calculate. Okay, so but this does not help per se to solve this problem because you still have this f plus g. And I think in the next exercise, Max is trying to convince you that it's really, there's basically no way from knowing prox operation for 2 terms, then also to know the prox is a sum. So for something that's simple, for example, for the derivative, if you know the derivative of two functions, you know the derivative of the sum. For subgradient, it's not totally like that, but still something is true. But for the prox operator, nothing of that sort is true. If you have the prox of one operator and the prox of another operator, you still have no idea what the prox of the sum could look like. So there's not no idea, but you still have no way to calculate it in practice. So, but it may be that this function here has a nice prox operator, and this may still be smooth. Or at least you get good gradients, for example. So if you know the prox operator of a part of the objective and the gradient or good subgradient of the other part, this may be better. So the proximal method has a much better guarantee than the subgradient method, and then even knowing the prox of a part of the objective may help a little bit, and it does. Okay, so the idea is splitting. Split the objective into additive parts. And this idea actually not only applies to convex optimization, but also in other fields, splitting of algorithms or some operators is sometimes used. So, for example, if you want to solve operator equations, ax equals b, sometimes it's beneficial to write a as a1 plus a2 and try to do something to two things for these operators a1 and a2 differently. Okay. Into parts f and g, and then we may have favorable properties of these two parts. For example, one thing we're going to use a lot is L smoothness. This is the term which is basically exclusively used like this in convex optimization. So if g from Rd to R bar is convex, differentiable, and the gradient of g, which is now a map from Rd to Rd. Actually, I could omit the bar here because we want to have a differentiable everywhere. And we assume that this is Lipschitz continuous with constant L. I should write a little bit more careful with constant L. So what does it mean? It means that the gradient of g of x minus gradient of g of y in the two norm is smaller equal L times x minus y, again the two norm. This is what we call L smoothness, and it's so differentiable, and the derivative is 1 Lipschitz. So it's almost 2 times differentiable, but not quite. That's a very good property if it comes to optimization problems, because if you consider optimization problems, convex ones, so the minimum is here, and as soon as you're differentiable, you know that close to the minimum, the gradient has to be small. But it still may be that the function may look like this. So it's very, very steep, and then it goes here. So then here again, it's still the same, because it's still convex and smooth, close to the minimum. The gradient has to be small, but in this case the gradient has a very large Lipschitz constant, which means very close distance, the magnitude of the gradient may change a lot. So still a small gradient does not tell you how far you're away from a minimum, for example. And if you know that, this really helps, that if you know that the gradient is small, that you're actually also close to the minimum. At least by minimum value. Okay, and the other property is proximability. Proximability. And this is kind of not so strictly mathematically defined. What this does say that f may have, or f has, not may, because we want to define things, f has prox lambda f, which is simple to evaluate. Okay, so what does that mean, simple to evaluate? Yeah, well, we're still dealing with problems in RD, so we can think of each iteration step costing us some amount of time, and we can kind of consider how this amount of time depends on n. So for example, if So if the iteration step, for example, may consist of adding two vectors, like in the subgradient method. You have a vector and you have a subgradient and you need to add them together. That goes to D operations, basically, D additions. But in the context of this LAD last time, even the evaluation of a subgradient, for this you had to take first multiply by a matrix, a D times D matrix, which goes to D squared operation. You had to add the B, it's another D operations. Take the sign, which is a pointwise operation, again D operations, nonlinear but still fast, and then again apply an A transpose. So you have at least 2 times D squared operation, at least to get a gradient, which is quite natural. This happens in many situations, that getting a gradient goes to D squared operations. And then the hope is that the prox operator also can be evaluated fast, which means maybe in D operations. Or D square may be tolerable, but maybe not. Okay. So for example, in the gradient method, you always have the complexity that for each step, you need to get a gradient, but maybe of the order D squared operations. But if you now also consider the Newton method, you also have to solve a linear system. Okay, so up to now it's still not known how complex this really is, but all the methods which are available are kind of more expensive than at least than applying a matrix. Okay, so these are 2 favorable properties, and we're going to consider the case. And what is if we have both? So if we have this is proximable and this is L smooth, can we get something nice out of it? Okay, so the answer is yes, but I think we should do now the break. So a short break, a few jokes, and then I am back in 2 minutes. Okay, so here we go. So we want to use splitting, or we want to derive a splitting method, which can take advantage of the fact that the objective of a convex optimization problem is split into a smooth and L smooth part and to a proximal part. So first we need some more information of what we can get out of L smoothness. So if G is L smooth, which means just that the gradient is L Lipschitz, and we don't need not necessarily convex, just L smooth. Then we have the following. Then we know that the this term here, which is actually the first order Taylor expansion basically. So this is g of y minus the first order Taylor expansion at x. This is kind of a g minus its linearization. This is then has an upper bound of L over 2 times x minus y squared. So it says that if a function is L smooth, the distance between the function and the linearization does not grow faster than quadratically, and at least decays quadratically if you go to the point where you do the expansion. So this here is the point x, and this here is the y-axis. That's g of x. Okay, this is what L smoothness says. The function cannot kind of depart from its linearization too fast. And you may remember that in case of convexity, you also have a lower bound. If g is convex and differentiable, then this is the tangent. This is always the tangent always lies below the graph. So so this is kind of yeah, this shows that this here the difference here is always positive, which means that this line is below, and this upper bound says here that you have a square kind of a parabola above the graph, which is kind of L as its wideness somehow. Okay, so which means that really in this case of L smooth and convex, the function is really nicely kind of squeezed in between the linear function below, of which you know the slope, and the quadratic function from above, of which you also know the wideness, the parameter of the parabola. Okay, so we don't have to prove the lower bound. This is already clear by convexity. Let's only deal with the upper bound. And this is now the following. It's actually basically fundamental theorem of calculus again. And it goes like this. You rewrite this guy here as an integral. And it is the integral of 0 to 1 over the gradient of g of x plus tau y minus x inner product with x y minus x d tau. So and why is that? This is because this here is actually the derivative of the tau of g of x plus tau y minus x. If you take this derivative, it's exactly that guy here. And then you see that you're integrating a derivative, and what you have to do is evaluate at the end. Tau equals 1 gives you this, tau equals 0 gives you that. So this here is this, and this is also just an inner product of something with y minus x, and so you can just put it under the integral because the integral goes over unit interval. So this is actually the same as the interval from 0 to 1 over gradient g x plus tau y minus x minus gradient of g of x. Okay. So what you're going to do now is you use Cauchy-Schwarz. This gives you a difference of gradients at two different points, and the difference of x and y. So Cauchy-Schwarz. And now you're going to use L smoothness. This guy here, so this is gradient of something minus gradient of something. It's bounded by L times difference of the somethings. And the somethings here, let's do it like this, is this minus this, x plus tau, x minus y minus x. This x goes away. This is actually norm of tau, y minus x. And L from the Lipschitz constant. Okay, so in total, of course you can pull the tau out because the tau is between 0 and 1, and you see that you end up with, so you estimate it, what can go out of the integral, and L goes out of the integral. Also a norm squared goes out of the integral. And we're going left, yeah, we left with actually only the integral from 0 to 1 over tau. The tau, which is actually 1/2, and that is what we wanted to prove. Okay. L smoothness says that the function cannot kind of depart from its linearization too fast, not faster than than a square. Okay, so L smoothness also helps a lot. Like the proximal point or the proximal step guarantees that you reduce the functional value. If you have an objective of f and do a prox for f, to reduce the functional value of f. So for L smooth, maybe that for the function g, it's simple to do a gradient evaluation, but not simple to do a proximal step. Okay, in this case, if you have L smoothness, you can also guarantee a descent by a gradient step. And this was something we could not do for the subgradients. So for subgradients, you cannot guarantee. So if you move into a direction of a negative subgradient, you cannot guarantee that you get a descent actually. At least not without further checking of something. So, but for L smooth, it's simple. So, and how does that work? So L smooth functions allow for simple descent steps. So how does that go? So we write down x plus, so kind of we're going to move to from x equal to x minus lambda gradient of x, gradient of x. So what you want to show, what you'd like to show is that the function value here is smaller than the function value there. So this is what we like to show. Okay, what we do is we use this lemma here, 12.4, with x plus is equals to y. And what we need, what we get then? Then we get, so we do it like we bring these terms here to the right hand side, and then we get g of x plus is smaller or equal to g of x plus gradient g of x times x plus minus x plus L over 2 norm x plus minus x. So now, and what we see here is x plus minus x. What is that? We look here, x plus minus x is actually the negative gradient, lambda times the negative gradient, which means that this guy here, this is minus lambda times the gradient, which means that, oh, and this is also true here, right? This here is also minus lambda times the gradient of x. So, and in total what we get, so this is g of x, this gives you minus lambda norm of the gradient squared, plus, so here is also lambda gradient g inside, lambda goes out quadratically, but the minus sign is gone, okay, but still it's L times lambda squared over 2, and then still the norm of the gradient g of x. Okay. So we collect the terms here and get g of x minus lambda times 1 minus L lambda over 2 times gradient g of x. So we check by multiplying out, this gives minus lambda, and these two here give plus L lambda squared over 2, which is that one. Okay. So, and what do we see? We see function value at the next point where we moved by a gradient step is the old function value minus something, and as long as this something here is positive, we have guaranteed descent. So, okay. So what we need, that lambda times 1 minus L lambda over 2 is positive, which means that both are positive, which means lambda is positive, but also and 1 minus L lambda over 2 is also positive. And this is the case if and only if lambda is positive, and this here rearranges to an upper bound, it rearranges to 2 over L. So that's now nice. It says that you get a guaranteed descent in the function value. We only need to know the Lipschitz constant of the gradient L. And then if we take a step size which is smaller than 2 over the Lipschitz constant of the gradient, we have a guaranteed descent. So we don't know how much, and it's getting less and less the closer we move to the optimum, because then the gradient norm gets smaller and smaller, but that's how it is. So it's okay. It also has to get smaller and smaller because, well, if we move closer to the minimum, there's only not that much left anymore what we can do. Okay, so now we have two things. If we now consider minimizing f plus g, we know that in the proc step for f's with any step size guarantee descent only for f, unfortunately. But a gradient step for g with a step size not too large also guarantees descent, but only for g. Can we make something out of it? Okay. Okay. So one idea is the following. We have this minimization problem which would look like this. But what we do is now we're aiming at the iterative method, so which means that we have a step, a guess, xk where we are, and want to improve on that. And what we do is we linearize g. So we do this, say that it's approximately, and actually it's not approximately, it's even better. It's even an upper bound, is it? Yeah, it's an upper bound. So by the previous lemma, we have not an approximation, but even an upper bound by f of x plus, and then we replace this by the linearization at given xk, which means we to get g of xk plus gradient g of xk times x minus xk, and to get an upper bound, we have to add this L term here. So this we can do. Then we have distorted our minimization problem. We have not f plus g anymore, but f plus this term here, and it's an upper bound. So we know that the minimization of this will be worse than minimizing this in total, but it may still be better where we started. Okay, so we replace that, and then we just consider this problem here. So we consider xk plus 1 shall be an element of the minimizer of this guy here, not of that anymore. So it's f of x plus g of xk plus gradient g of xk x minus xk plus L over 2 x minus xk squared. So that's our step. That's the idea. We make use of the fact that the linearization of g is good. It's close to g because g is differentiable. And it's also not only good, but linearization plus a quadratic term of a size we know is even an upper bound. So this is the smallest square we can add to the linearization, so that the linearization gets turned into a quadratic upper bound. This is the best thing which you can do to majorize g of x if you want to do it by a quadratic function where the quadratic term goes like this. Okay, good. So then we are only interested in the minimizer, which means this term does not actually play any role. It's just a constant shift because xk is fixed. Okay. Yep. So and what can we do? Is it now possible to minimize? And it looks like yes. It looks like it should be not too difficult because we have f of x plus a square here. So these two terms together would just give the prox, but we still have this linear tilt here. If this would not be there, this would be exactly the prox step with a constant 1 over L. 1 over L? Yeah, I guess so. 1 over L. Now let's keep it with the 1. I think in the handout, in the lecture notes, I've written here 1 over 2 lambda. But let's keep it like that. Let's work with L. So in the lecture notes we have L is equal to 1 over lambda, and one could also do it like this with a step size which does not depend, really is not tied to the Lipschitz constant, but let's do it like with the L. It's also the same thing basically. So what do we do now to get these things together here is we add and subtract 1 over 2 times lambda the gradient g of xk. Actually, we can also add it because it's just about the argument. So maybe let just let us add it because it's not an effects minimizer. So what this is we're completing the square. That's lambda. It should have been 1 over L. This completes the square, and actually, so one more thing is I've written it is an element of, but actually we could also write equal to, because this is a strongly convex function here. This is convex, linear, strongly convex. In sum, it's strongly convex, so the minimizers are unique and also exist. Okay, next step, we write out what the completed square here is. Somehow I missed right sign. No, it's fine. So the completed square will then be plus 1 over 2 x minus xk plus 1 over L gradient g of xk. Okay, that's the completed square, and you can just check multiplying out, or it's just like this. Sorry. Oops. Yeah, no, that's not true. Actually, we have an L over here. Like this, it should be right. No, sorry. Sorry, I screwed it up a little bit. What do I want to do? Yeah, this was not totally right, so let's do it again. Actually, it was not totally wrong, but it was not like I wanted it to have. So one step back. So what I so actually, completing the square is the right idea, but it's probably nicer to multiply through by 1 over L. So because it's just the minimizer, and let's do it just in 2 steps, so it's not getting too confused here. We multiply through by 1 over L. 1 over L gradient g of x, k, x minus xk plus, no, it's no 1 over 2, just 1/2. So like this. That's better now. And now we complete the square by adding just the norm square of that. 1 over 2 norm square 1 over L. So that's how I wanted to do it. So if you complete that, it gives us arg min over x still of 1 over L f of x plus, and then we have 1 over 2 times the norm of x minus xk plus 1 over L gradient g of xk. Okay, and you probably gonna recognize this, what we have here. What we have here is minimizing for convex function times a constant plus the squared distance from the x to something. That's the prox. This here is actually the same as x minus xk minus 1 over L gradient g of x. So this is this full term here. Let's go use this. And so this here is exactly the prox of 1 over LF of xk minus 1 over L gradient g of xk. Okay, so this is something to remember. And this is now interesting because it kind of really combines the two things which we can do. What is inside the prox operation here is the gradient step with a step size 1 over L, and remember what our step sizes should have been in between 0 and 2 over L. So it's right in the middle. Seems like good. So we do a gradient step for G and then a proximal step for F. and note that these two guys here are coupled. Okay, so this is the so-called proximal gradient method. We're going to analyze it. It takes some time, so we can't do it in the next lecture, unfortunately, but we're going to analyze it in a few lectures. And it can kind of combine the ideas of gradient descent of in the proximal method. And we're going to show that it actually works. And this is now nice because it kind of can use the best properties which we have of the two terms we have in the objective. So if one of them is L smooth and the other is proximable, we can do that, and it's not that bad. Okay, so analysis of this is postponed. But I'm going to show you an example of where this is really actually helpful. Okay, and I think this example, then that's it for today. So the example is regularized least squares. So we know about least squares. So let's say we have an operator, or the matrix M by N, and a vector B in Rm, and then you can already know the least squares problem. You minimize 1 over 2 ax minus b 2 norm squared, which is still good. So if for example, if your system is overdetermined and it's not consistent, you can solve ax equals b, but you still may be able to solve that problem here. It's used in regression, but it's also used in lots of applications. And whenever you have measurements of something, which you want to by way of ax equals b, so you have measured b and you know how to measure it by a, but you want to know x. So overdetermined, so too many measurements, inconsistent ones, you can do this. But why should you do it? If b is a measurement, then there's some error on it, and you just would not like to have this zero. It just really doesn't help. So in practice, so let's say b is a measurement of unknown x by a. So that's kind of the setup. So, but in practice, you have measurement error, which means what you get is not ax of some unknown x dagger. This is how we're going to, so x with a plus over the dagger up here. So what you have is not b, but you have something which is often called b delta, which is actually a of x dagger plus some eta, and eta is noise. That's basically always the case, as always. So like this microphone measuring me speaking here, there's it's an analog to digital converter involved, and there's kind of the sound wave is converted into first into an electronic wave, and then into a digital signal, and there's noise involved all over the place. Same for the camera here. It's always not, but the camera is pretty good right now, so there's basically no noise here. But actually, I'm not really sure. So probably there's some noise cancelling going on here up in the camera already. I don't know. Okay. So there's always noise involved. So this b is always never really accurate, and solving ax equals b delta doesn't make too many sense. So solving does not. Let's write make too much sense. It depends. No? It depends now on the properties of a. You probably know about the concept of condition number. The condition number is the norm of the inverse of a divided by the norm of a, or if the inverse does not exist, the norm of the pseudo-inverse divided by the norm. And it kind of measures how sensitive is the solution of a linear system or the pseudo-solution to errors on the right-hand side. And so linear operators tend, at least the ones I'm going to work with, or usually work with, have the property that these linear operators may have a huge condition number. So, and even for small matrices, let's say 10 by 10 or 100 by 100, it may be 10 to the 6 or whatever. Which means as soon as you have a slight measurement error here, the errors, if you solve this, get amplified, multiplied by the condition number somehow. Okay, so this is one thing, and also minimizing AX minus B delta as well. That's the same thing. So why would you ever try to come close to B delta? So not coming close is fine, but being equal to B delta, that's asking too much. B delta is wrong anyway. Why should you gonna go for it and really solve AX equals B delta? It depends on a lot of things. So this is probably too simplistic. But if you have a fully determined system, A is square and has full rank, then this is really a bad idea. If A is, it's really a bad idea in general. Because then kind of the condition kicks in at full scale, and you really get more or less the worst noise amplification which you can get. Because you don't have you can't do anything. You have a consistent and full rank system, and there's only one minimum of this. That's it. And so each equality, this is kind of a number of m equalities here, and each of the equalities just gives you just enough information to solve the system, but nothing more. And this kind of, you can't leverage anything about having different measurements, giving different information. They just give enough information. If you have an underdetermined system, so not enough measurements, m is much smaller than n, then this is not too bad anymore, because you still have a lot of freedom here. So you may minimize it if you would like to, but you still have a large null space. So there's still a large null space in A, which means that for any solution X you can still add a lot of things which may help to pick a good thing, a good solution. So in the underdetermined case, minimizers may not be that bad. In the overdetermined case, where A is tall, so we have much more measurements than degrees of freedom, then it may also not such a bad idea to solve it, and also to really solve it, because you can't drive it to 0 anyway, because the system is usually inconsistent. Different measurements with different errors may lead to an inconsistent system. And also you have more measurement than you need to solve the system. So there's different equalities telling you different information, you have more than you need. And in the largely overdetermined case, it may be the case that solving this is not as bad as it looks. But at least in the case where you have kind of around the right number of measurements which you would need to solve, in the case of noise, that's a bad idea. So going for as much as right enough measurements for what as you can get, that's usually not good. Okay, so what I'm getting a little bit off track here. Let's so what do you do in the case where you have kind of about enough measurements? You really don't want to do that. So what you can do is regularize the problem. And by regularize means you come up by yourself with a regularization function. It's called regularization functional R, which maps from RD, not RD, sorry, we are in Rn now, from the space where the X comes from, and maybe to the extended real numbers. And the rationale behind this should be that R of X is small for, let's say, reasonable X, and large for let's call them undesired or unreasonable X. So if you have a means in your space of solutions, kind of assign a value which tells you a priori how good the X is in general, without knowing anything about the system. So for example, signals may be smooth, and the R could be like, it gives a large value to non-smooth signals, small values to smooth ones. Maybe 0 to all the constants, and the more it oscillates, the larger the X. Or you just say, well, this X, in general, the norm is not too large. So, for example, if you take the L2 norm, so the norm of the entry squared, the square root of that, then it's kind of the energy in the signal. The signal has bounded energy. So you can, for example, and the larger the energy, the more unreasonable it becomes. Which is, for example, true for the noise, for the sound signal I'm just emitting here. It does not have zero energy, but if I don't speak, the energy should be zero, but you probably still hear noise because the laptop is making some noise here because it's it's making noise all the time. But of course, the energy I can emit is bounded, so having finite energy or regularized with the energy is not that a bad idea actually. So that's a priori knowledge. So without knowing anything about the measurements, we would still need to come up with something which shows a priori these kind of things is what we would not like to see as a solution. And what you can then do is you do not minimize the least squares functional, but you regularize in the way that you add your regularization functional with some positive regularization parameter. So now we have a trade-off. The trade-off, also this is delta here, trade-off between explaining your delta, explaining your measurements B delta, and being reasonable. And if alpha is large, you said, well, I need to be reasonable. This is what I need to do. And if alpha is small, you said, well, I want to explain my delta, my B delta. And with weighing alpha between large and small, you can tune between what's more important, being reasonable or explaining the data. So that's the so-called regularized least squares problem. And of course, what we like to do is, would be nice if there was convex. Okay, this would be especially nice because then this would be a convex function in total, and all the things we done apply. And what would also be nice is if it would be proximal. Because then we could apply the proximal gradient method here. Also, of course, we would also like to have it LSC, lower semi-continuous, otherwise it would be strange. It would probably be strange. It would not, then it can be the case that you have a sequence of converging x, lots of reasonable x, but the limit x would be unreasonable because the function value could jump up. What lower semi-continuous allows is that you have a sequence of functions which becoming more and more reasonable, but in the limit it's even more reasonable than what you expect. Okay, that's nice. Okay, so we split this. We write it as f of minimize f of x plus g of x with it's the other way around with the g of x. That's the smooth part, 1 over 2 ax minus b delta 2 norm squared. And as f of x, we take the regularization function. That's smooth, and that's proximal, hopefully. So but we can design R as we like. So we can choose it like it's proximal. We can do it if we want to, because it's it's our choice. Yeah, and then what we need to do to write down the proximal gradient method is the gradient of g of x. What is that? You probably know that. I don't know. Do you know that? How do you calculate it? Actually, I've done it before. It's also, so you can deduce it from the chain rule, but transpose because we have the gradient, not the difference, the derivative. Okay, but anyway, it goes like this. The 2 goes away by differentiating. You get an A transpose to the left because gradient is derivative transposed times A x minus b delta. And then this is actually Lipschitz. Why is this Lipschitz? So if you just do gradient of x minus gradient at y, this is plugging this guy here in. It's A transpose A x minus A transpose b delta, but this goes away with this guy here. It's actually like this. So because this minus A transpose b delta pops up in both of the terms and cancels out. Okay, and then that's just now clear. It's just by the spectral norm of A transpose A times x minus y. So this here, that is the best Lipschitz constant which is there for the gradient of this g. So kind of G is L smooth. Okay, nice. And now we can write down the proximal gradient method. This would be xk plus 1 is equal to the prox of, and now we take general step size lambda, and so we have to multiply this guy here by lambda, so it's lambda times alpha times r of xk minus the gradient step with step size lambda, which means minus lambda times A transpose axk minus b delta. And what we need is, so at least for the gradient step to be reasonable, we need that this lambda is between 0 and 2 over norm of A transpose A. So that's nice. So what's nice about this, so you can design the R as you like, and as long as the prox is very nice it's simple to evaluate, then you only need to know the norm of A transpose A, which is the same as the norm of A squared. So you need the largest singular value of A, or the largest eigenvalue of A transpose A, which may be approximated numerically by the power method. It's not so hard. Sometimes it's tedious, but it can be done. But as soon as you know this, you can just choose any lambda in this interval and always get a convergent method. So we didn't put convergence yet, but we're going to do in a few weeks. And it always works, and it's a one-liner, right? It's a one-liner. So once you implemented the prox operation, this is just basic linear algebra, and any reasonable mathematical programming language can do this in just without no effort. So that's nice. So you can solve regularized least squares problems with a proximable regularization functional, just like that. Okay, granted, it's not always the fastest method, but for non-smooth R, it's even remarkable that you can get such a very, very simple method which is guaranteed to work. It's not guaranteed to be fast. There are guarantees, but the guarantees are kind of slow. We come to that. And there are better things to do, and even more reasonable, more remarkable than this is such a simple one-liner which always works, always, as long as you don't do anything wrong by implementing, is that there's an even better method, which is only very slightly more complicated, but it's much better in general, and you can prove that. And it's better in the sense that it only needs this very simple operations, and so does a few more additions and nothing else, but it's probably much better. Okay, that's it for today. Next week is the break. There's no lecture, no exercise class, no new exercise sheets, no nothing next week. Just take a break or kind of recall what we've done up to now, and then after that we resume with the second half of the lecture. But actually, it has been lecture 12 today. The full course has 28 lectures, so there's 2 more lectures to come before we come to the break point where the semester is split into 2 halves. Okay, and in the next week, which is the last week of the first half, we will finally do some duality theory, but unfortunately we cannot develop the duality also in optimization framework because this will take us cost us too much time. So in case you want to know more about optimization algorithms, how to apply them in practice, you should stay and visit and listen to the second half. Because there will be many more practical things in the second half to really help you solving convex optimization problems. Okay, that's it for today. Have a nice break, and see you after the break.